Alright, testing. Everything good? Cool. Welcome back. Probably a short video today because I have work and I got a lot of stuff to do. But probably at work I'm gonna code a little bit more because I never do shit. So probably work on my portfolio and yeah, hopefully soon I can show you guys my portfolio. It's not done. It's pretty shit right now. I'm trying to learn. But yeah, thank you for all the support again. I just want to show you guys the video's been doing insane, man. You guys got me 64, 154, like, you know, we're in the hundreds now, so it's like not bad. So if you're watching this, I really appreciate you for your support. Yeah, it means a lot to me. So yeah, I guess we're on day 11. Been doing this 11 days in a row. But yeah, let's stop yapping and get back to where we were. As you can see, we were right here. I don't know when I gotta go because I gotta wait for a text from my mom because she needs me. So until she texts me, I'll keep going. So it'll probably be a fast today. I don't know when I'm gonna do longer content. I really want to do longer ones, like an hour to 2 hours, but yeah, we'll see though. Yeah, my boy Noah does this all the time, so he's been working lately. So I don't know how long his vids usually are. Like ranges from like 15 minutes to an hour. What's his longest vid? I'm curious. We have an hour 21. 2 hours. Dang. Yeah, he grinds this stuff. Good inspiration. So if you're watching this video, support my boy as well. Anyways, alright, back to what I was gonna do. Alright, so constants don't matter. Big O notation only describes the theoretical growth rate of algorithms. It doesn't deal with actual time an algorithm takes to run on a given machine. As such, when Big O analysis, we don't let ourselves get bogged down in details. For example, take a look at the following functions. Print names once, so names, so for name and names, print names. So it's printing all the names once. Print names twice, so for name and names, print name, for name and names, so it's 2 for loops. So this means, as you expect, print names once would take half the time to run, right? Because it only has one for loop. And in the real world of software engineering, cutting speed in half is awesome. The funny thing about Big O, where are we? Funny thing about Big O analysis is that we don't care. We're academics. I don't even know what that means. Both of the functions above have the same rate of growth, O of n, right? You might be tempted to say print names twice should be O 2 times n, but you would be missing the whole point of Big O. In Big O analysis, we drop all constants because while they affect runtime, they don't affect the change in runtime. Give me 1 second. Okay, cool. It might be tempted to say, print names should be. Oh, okay, where were we? A constant affect the runtime, but it doesn't affect the change in runtime. So O of 2 times n is O of n. O of 10 times n squared is just n squared.
Big O notation only cares about the theoretical slowdown of an algorithm as its input size grows. It doesn't actually care about how long, like in seconds, this algorithm is going to take to run. So when I say if a linear time algorithm takes 1 nanosecond to run with an input size of 1, then it will take about 10,000 nanoseconds to run for an input size of 10,000. Like, that is true, but whether or not it actually takes 1 nanosecond on an input size of 1 or 1 full second on an input size of 1 is actually completely irrelevant to Big O. All we care about is the proportional change from 1 item to 10,000 items. We don't care about how long it actually takes. And when I say we don't care, I mean we don't care as computer scientists doing this theoretical exercise. Of course, as software engineers, we care. No one cares if the Big O of your website's load time is constant. If it actually takes 5 seconds to load, that's a terrible experience. So as software engineers, we do care about constants. But when we're doing Big O analysis, we don't really care. We just kind of brush it aside. We hand wave it away. Say you have a function running in production, and it takes 5 seconds to run on an input size of 10,000. Then you benchmark it again on an input size of 10 million, and it still just takes 5 seconds to run. Well, that's actually a constant time algorithm. The runtime isn't being affected by how big the input size is. But whether or not 5 seconds is actually tolerable by your users is up to your users, I suppose. But why this matters is that 5 seconds in big O terms, we just don't care. We don't say, oh, it's order 5 because it took 5 seconds. We just say it's order 1 because it's constant. So that constant can always just be reduced to 1. Let's take a look at another concrete example. Here we've got a function called sum. Takes a list of numbers, iterates over all the numbers, summing the result as it goes, and returns it. This is fairly obviously an order n algorithm. Now this is interesting. Let's say we take another function. This one's called triple sum. It iterates over every item in the input once, summing the items as it go. But this time, it does it again and again. So just looking at this function, you can tell this function takes 3 times as long to run as the first one.
Right.
Instead of looping over the input once, we're doing it 3 times. So if the first algorithm is order n, wouldn't this one be like order 3n?
Yeah, because
and the answer is yes, but we don't care. We're doing big O analysis. Constants don't matter. So that 3 just reduces to a 1, and we get order n again.
I guess. Good to know. Which is the proper big O classification? How would we reduce O of 2 times log 2 times n? O of log, hold up. Oh. Thing is O of log n. Yeah. Holy shit, were we supposed to? No, okay, this is different. Constants quiz. Consider the following. Okay, so this one adds and this one is double. Whoa, okay, wait, hold up. For num and num's total plus, we're just adding on to the next. Okay, now double sum of total for num and num. Double equals num plus num, and then we add the double. So say it's 1 equals 1 plus 1. The next one's 3. 3 plus 3, then that's okay. That's constant though. Yeah, they're both constant as I guess what the video is saying. Ignoring the big O theory, which function will realistically take longer to execute? Double sum. Alright, okay. We're getting the hang of it though. We're getting the hang of it. Alright guys, my mom be texting me, checking on me. Order 1. O of 1 means that no matter the size of input, there is no growth in the runtime algorithm. This is also referred to as a constant time algorithm. In Python, a dictionary offers the ability to look up by key, which is an operation that is independent of the size of the dictionary. So, this is a constant time lookup. Org is organization's org ID. Okay. Cool. Assignment. We need to be able to search. Okay, so the assignment. Okay. We need to be able to search our logged in user base more quickly. So we need, okay. Our users are complaining that the search bar is painfully slow. You'll notice that if you run the code on its current state, it'll take very long. The find last name function takes names underscore dict a dictionary of first name to last name, first name a string. If first name is a key in the dictionary, if it's a key in the dictionary, find last name returns the associated last name. If key is not found, it returns none. Write the function so that it runs quickly. It should be O1. I guess if we run it, it's gonna take long, and it fails. Less than 50 milliseconds. Okay. So for current first name, last name, I'm not understanding this. For current last name in names underscore dict dot items. Hold up. It's searching up the searching up. So find last name is it takes in names dict, a dictionary where keys are first name and values. Oh, okay. Okay. So last names in for current first name. Last name in names underscore dict dot items. If current first name is equal to the first name, return last name. So first name is a string. Oh, so what it's doing is so names underscore dict is like John Doe, Jane Smith. First name example is John. So it's iterating through all the last names. Sorry. Is it? Wait, hold up. This loops. Okay, yeah, this is the one that I'm like a little bit hesitant about. So this loops to each key value pair in dictionary. Current first name is like the key, like John. Last name. Goddamn. Is the value like Doe. Okay. If current first name is equal to first name, if it checks out if the current key matches the first name we're searching for, it returns the corresponding last name. Example. Find last name. John equals Jane. No. Jane equals Jane. Return Smith. This function is less efficient than just doing. So it works. Okay. So now what is it asking me? We need to be able to search our logged in. Okay, it's slow. You'll be noticed of the code. Yeah, okay. The find last name function takes yes, okay. If first name is a key in the dictionary, find last name returns associated last name. If the key is not found, it returns none. Write the function so that it runs quickly. It should be O of 1. So what does the dot items do? Oh, that's for both? Analyze method does not take any parameters. Return. It should It returns data on its view object, which is iterable to. For current first name, last name, this means current first name gets each key from the dictionary's first name. Last name gets the corresponding. So names underscore dict. Out returns Alice Wong, Bob Smith. So this loop does Alice's current first name. Where are we? Damn. First name is a key in the dictionary. Returns associated last name. If key is not found, it returns none. So names takes okay. So the find underscore name, and then names underscore dict is a dictionary of first name to last name. And we need to check if the first name are the same. How do we check if the first name? If current first name. Hold up, bro. Bro, leave me alone. For first and I want to see if I can iterate through the indices. It gives me Alice. I don't know how to start this. It's probably so easy, I'm just not fucking getting it. Are you usually complaining this is yes, I know. Yeah, this is a constant time lookup. I get it, but think you guys know what I'm going with this. So for first enlist namesticks. If first is equal to first name, return names ticked first, which should be that, the last name, and then if key is not found, else return none. Hold up. What? Damn, this one took fucking long. How, if it iterates to the first, is that what the other one was doing? Code below is what I have so far. Please let me know if Yeah, I have two IDs. Oh, no, that's... You're currently checking the first name presentation. You're currently returning the last name. Hit on what to approve. Right now, you're using a loop for which takes the time collection. It makes sense. So but what? How? If key hold on, I'm so sorry. So if key in list names ticked. How do you copy a line? I want to know how you copy a line. Oh. What was I doing? What did I do for first? I can't do that. Oh, I think I have an idea. If list is Hold up, I'm tripping. No, bro, what am I doing? Why would I do that? If first name. Oh, first name. Oh. What? Hey, but this one work? I guess this one has more inputs. I don't know. I have no idea. Excuse me, sorry. Where am I? Ah! I don't know. I don't even know. Fuck. So saying that this is what's slowing it down makes sense because it creates a new list. And then... because you have to go through the... in... Dictionaries in Python already allow if some key in some dict. That checks all. Let me see if Google. I don't want the answer. I just want to see like examples. A get method? No. Ah, I don't know. Oh, fuck. So this just checks if that's in there. I just made a whole list and then and that iterates through it. This just checks. Makes sense. I can't submit yet because I do have an issue if the key is not found and returns none. I think if I put else return none, it will be fine. Pass. Okay, cool. Not bad, I guess. I don't know. Fuck. I don't know why I made the list. Because when I read about it, if you do list for X and list here, print X, it does that. So what if I put for X? Same shit? Damn. Never mind. I thought list just gets the key. There's no need. I guess we learned something new. What we got? I think I gotta go. So we'll stop here. I'm gonna do these two on my own today at work. And then the next thing we're gonna do is sorting algorithms. So I guess we're getting into the gist now. So yeah. Yep. Alright boys, I appreciate you for clicking the video. It means a lot to me. If you learned something new, give a like or comment, say I learned something new with you or something. I don't know. I appreciate you for clicking. This is day 11. I'm trying to get better every day. Yeah. I need to do a little bit more of this. So hopefully when I get some downtime, I'll do this a lot on my own. But yeah. I appreciate you for clicking the video. It means a lot to me, and thank you for anybody that stayed this long and all the support. So yeah. Alright guys, see you later.